Welcome to Argonne at Lunch. I'm Justin Bro with Media Relations and External Affairs here at Argonne National Laboratory. Do you ever think about power? Maybe you're watching this on your tablet, your phone, or even your laptop, but I'm not talking about that type of power, and those are batteries. Today we're going to be talking about batteries that power big things. So think about transportation. Think about electric vehicles and the electrical grid. So we're going to be talking to a researcher today about how she works with supercomputers and other researchers to create next-generation technologies to not only have our electrical vehicles go farther, but provide resiliency to our electrical grid. Why don't you follow me this way? So there are about 200,000 miles of wires for our electrical grid. And for electric vehicles that are becoming more in vogue, there is an issue with a price point for how much they cost. Since the battery is the most expensive part of the car, what researchers would like to do is find technologies to be able to bring that price point down to make it more affordable for people like you and me. And one researcher that we're going to talk to is named Lei Cheng, who's a computational chemist here at Argonne National Laboratory, and she's right over here. Hey, Lei.
Hi, Justin.
How are you?
Good.
Excellent. So I have one question for you. This is my first question, actually.
Okay.
What is a computational chemist?
Computational chemist is I use supercomputers to model the chemistry, the reactions, and the material properties. So it's computational chemistry is a branch of chemistry where we use computer simulations to do these research to study materials and chemistry.
And what classes did you take in college, university to help you get to this point?
So for my undergrad, I just did a very basic general chemistry major. And then for my PhD study, I think the core courses you have to take for computational chemistry is theoretical chemistry. You have to know the theory that's behind all the computing and simulations and to know that. And
so like these theoretical chemistry classes that you're taking, so they're basically supercomputing prep classes?
Not necessarily. There are theories actually preparing. You have to understand the theory, the quantum chemistry behind those theories to understand what you're doing first. And then some computer courses, of course, basic Linux skills and basic coding skills that help you, that give you enable you to use the tools to do.
So you're not only a chemist, but you could program computers too. Is that what you're saying? Yes. I might need to take some classes from you. So where did you go to school?
I got my undergrad in applied chemistry from China, actually, Qingdao University in China. And then I came to the States for my PhD study. I went to Southern Illinois University at Carbondale for my PhD study. Go Dogs.
So like when we talk to people, they always mention people in their lives that made a difference for them, that helped them on the path that they are. So did you have any really outstanding mentors that help you be where you are?
Oh, I have so many outstanding mentors. I have my PhD advisor and my postdoc advisor here at Argonne that helped me a lot throughout my career with my academia and provided a lot of guidance to my career development as well. I have a official mentor here in our division too that she's given me very, very good advice on my career development. And
Do you want to call her out by name?
Amanda Petrit-Long.
There you go, Amanda. Thank you.
Yeah, thank you, Amanda.
All right, so if you're joining us, we're here at Argonne at Lunch. We're talking to Lei Cheng, who's a computational chemist here at Argonne National Laboratory. Now, the work she does goes into thinking about and testing the next generation batteries that are going to have applications not only on the electrical grid, but in transportation. So if you do have any questions or comments down here, where's my finger, Don? That's right, it was? Okay. So below this area, go ahead, add your questions or your comments, and we'll get right back to you live. That sound good? Thank you very much. All right, so our next one is, all right, so this is one that sometimes I struggle with, but you probably know. What's the difference between the Joint Center for Energy Storage Research, or JCESR here at Argonne, and Argonne's battery research that goes here at the lab?
So Argonne, as you know, has a long history as a center for energy storage research. So we have a very large and diverse battery research portfolio, ranging from very fundamental research to a more applied research. So JCs are specifically focused on the very fundamental side of things. We do discovery science, while some of the other programs are more applied focus. So you talk about engineering and manufacturing and scale up side of things. And also our focus is beyond lithium-ion batteries, while a large portion of the other programs here focus on lithium-ion battery.
So if I can wrap my head around this, so JCs is particularly focused on beyond lithium-ion, is I have that correct? So what types of things are you doing? So I imagine you're working with different types of chemistries and melding those together to see what works, right?
Yes. So we have two main focuses with the JC's research. One is we wanted to study battery for the next generation of transportation. So those are the batteries that you can put into your cars and for electric vehicles. Another main focus is a large-scale utility scale grid storage device that you can plug into your grid, so that when you have intermittent energy resources such as wind and or solar, the wind doesn't blow at all time and the sun doesn't shine at all times. You want to be able to store these energies and during peak usage hours and release them to the grid. Yeah.
I think I've heard that before. So that's called distributed energy. So you'll have like a large battery that, just like you said, you have solar or you have some other type of device that's renewable connected to the grid. You can use that energy either live or you can store it, and then when you really need it, say the power goes out, you can go to the batteries for supplemental power, no?
Yes, exactly.
And so how does that, so let's go back to Argonne's battery research. So how long has battery research been going on here at Argonne?
I would say decades.
So was it before I was born? I'm 41 years old. Don't tell that to people, Don. But a long time, yeah.
A long time, yes.
And so I'm going to give you a really hard question. Why is battery research important?
Right now, just the two areas we're focusing on, right? So if you think about the cars that's running on the roads today, right, they're all gasoline-based, and we all know those are fossil fuels, and then we have a limited supply of fossil fuels. We wanted to be able to have a more sustainable way in the future to be able to run these cars on the road without, running out of the gasoline. And plus, we all know gasoline cars are not terribly efficient. I think it's only 30% of the energy you get out of the theoretical energy you can get out of the fuel that's being used.
So let me ask you about that. So you're saying if I pump a gallon of gas in my car, I'm only actually using 30% of that gas to power my car?
Yes, and some of the energy you have incomplete combustion, and some of the heat will get lost, and there are programs trying to optimize the efficiency of the gasoline engine, but ultimately your electric vehicle will be much more efficient, and plus the source will be coming from other renewable sources, greener sources such as wind and solar, and there's no emission involved. So that's just one aspect of why this is important.
All right, so let's move around a little bit. Let's just walk over in this direction because we've been standing too long, and I like to move my feet. So, but I do want you to tell me and explain to me a little bit about what discovery science is. So that's what you do, discovery science. But explain to me what that is.
Yeah, so the job that I'm tasked to do specifically is to do materials discovery. As we move on to different energy storage concept, we can't just move all the materials we use in lithium-ion into these new systems. We have to, because of the function and the conditions, those energy storage changed. You need to discover new materials to be used in those new storage batteries. And my research is to help discover these materials and to help study and understand how they behave and why they behave the way they do in those new systems.
So if I can wrap my head around that, so I'm picturing the periodic table elements, you know?
Yeah.
And so you're taking all those elements together and say, okay, well, this may work with this, but it won't work with this. Okay, this may work with this may work with it. And that's part of your research to find out what those reactions between those elements are
Yeah.
for battery purposes.
Or even just come up with the materials and try to compute their properties. And I have a set of criteria that I have, the requirements that those materials have to meet. And then use supercomputers, I can compute those properties and see who makes the cut, who doesn't.
One question, who sponsors your research?
This is the Department of Energy, Basic Energy Science sponsors my research, yeah.
And do you work with any awesome partners? Shout out to awesome partners right here.
Oh, I work with a lot of awesome partners here at Argonne, and also all across the nation. We have 20 partners that ranging from universities and other national labs and industry. I work closely with them.
If you're just joining us, this is Argonne at Lunch. My name is Justin Bro, but the more important part is this is Lei Cheng. She's a computational chemist here at Argonne National Laboratory. We're just talking about how to make the next generation battery possible. Lei Cheng does that by not only using elements, but different materials to come up with different materials for battery applications that have to do with the grid and for vehicles. So if you do have a question or you do have a comment, go ahead at the bottom of the screen, wherever that is, and go ahead and leave a question or comment, and we'll get right back to you live. I'm not going to use that one. So you use supercomputers. How do you use a supercomputer with material science to discover new battery materials?
Right, so I have normally I have a database of molecules that I think could potentially, or materials that I think could potentially work as, can be put into a battery, it could potentially work, right? So to evaluate that, I use computational tools. So I will just go on my computer and then use a software to connect me to the supercomputers. I use supercomputers here at Argonne Leadership Computing Facility, the Blue Gene supercomputer, and also another facility that I use is a NERSC machine located at Berkeley National Lab. So I'll connect to those supercomputers and submit the molecules I wanted to calculate and reserve a block of the CPUs on those machines, and then to calculate certain properties of the molecules that's relevant to energy storage applications.
So why couldn't you just do this on your desktop computer?
Okay, so for example, if I have a molecule that I will run on my workstation or my laptop, that will take about a couple of months to finish. So we're talking about serious computing here. With the supercomputers, that's tens of thousands of your home or your PC computing power combined. I can just reserve a couple hundred processors or cores to work on the same problem at the same time in parallel. So instead of a couple of months, I will finish my calculation in a couple of days and have a very fast turnaround time. And that way I can do fast initial screening very quickly. Yeah.
So that's an endorsement if I ever heard one, of using supercomputers with big data to find solutions to really big challenges. So, okay, so you've done your material science, and you think you have a molecule that works. You want to sort of synthesize or you conceptualize that material. So you go to a supercomputer, and you put it in the supercomputer, and maybe it verifies what you were earlier assuming. So we're done, right? So all we have to do is pop that into a car and drive, no?
Yeah, only if we could just do everything on the computer, right? So we do have certain properties that we can do a very fast screening with a computation, but there are certain properties that we could theoretically do it with a computer, but it takes a very exhaustive, very comprehensive search. So at that point, it makes sense just for us to hand the materials over for our experimentalists to test, at that point.
So now we're talking about making the actual battery. And so what we're going to do is we're going to walk over here to one of our researchers at Argonne, whose name's Krista, who has been so gracious to volunteer her time. Hey, Krista, how you doing today?
Hi, I'm doing well. How are you?
All right. So what do you do?
So I actually build the batteries. Lei gives us a material. I go and make it. I make it into a cathode for a battery, and then I make the battery, and I test it, and I see if it works.
That sounds awesome. So this is your workstation right here. You're going to show us how to put together a battery, right?
Yes.
All right, so if you're watching us here at Argonne at Lunch right now, we're going to put together a battery. This is one of the coolest parts of my job right now. So why don't you go ahead and get this? And so why are we in this? What is this called? This box here.
So this box is called a glove box. And the reason we use this is because a lot of our materials are really sensitive to air, to oxygen, and to water. So we have to have an environment that is air-free and water-free to build these batteries. And then once it's sealed, then we can take it out and go put it on our battery cycler and it's fine. But
So no batteries are exposed to air or water, is that correct? Like the one on my phone, it's not exposed to air or water, is that correct?
the one in your phone is not exposed to air or water. There are some that are water-based, like the lead-acid batteries in your car. Those are water.
Not electrical vehicles, just my regular old gas guzzler, no.
Yeah, just the little battery you use for the starter, not the nice electric vehicles with the lithium-ion batteries.
EVs.
Yes.
All right, so let's check out this battery and take us through the process and explain to us a little bit about, so you've talked to Lei and you have an idea of the materials that you want to use to construct the battery. What's the process as it goes from there?
So the process that goes from there is selecting the other components. So for a battery, you need three things. You need a cathode, an anode, and a liquid electrolyte. So the cathode and the anode are where the reactions occur and generate the electricity. And the liquid electrolyte allows our magnesium ions, which is the type of battery we're trying to build, is a magnesium ion battery. It allows the magnesium ions to move back and forth between the two wherever they need to go for the reactions to occur. So we have our cathode material from Lei. So then from there we select an electrolyte to go with it. And for this, for most of our battery studies, we're just using magnesium metal as our anode.
Let's get to it. Let's check it out.
Yeah.
This is cool.
All right. So we're building a coin cell, which is really small, so called because it's about the size of a quarter.
Coin cell.
Coin cell. But it allows us to do testing with small amounts of materials, just because some of them are difficult to synthesize. So what we have here is we have the bottom of the coin cell, the top of the coin cell, and this is a plastic ring that goes in between and keeps the two sides separate. So that's what forces the electricity to actually go outside the battery rather than just straight across. So we put this, let me make sure it's the right side up. It is. So this goes right in here. Now our electrodes, our cathode and anode, are actually pretty thin, and this is pretty thick. So we have these, which are just stainless steel spacers. So they just make up the extra room. So we'll put in one of those. Next up is our cathode. So this is our cathode. So what we've done is we've taken the powder that we made and mixed it with carbon, and then we paint that mixture onto a piece of molybdenum metal. And
what is, that's a $20 word. What's molybdenum?
Molybdenum metal. Molybdenum is just a metal. It's in the middle of the periodic table. It's pretty stable, which is why we use it. It doesn't have any extra reactions that we don't want. So for us, it just sits there and lets the current pass through it.
And we use molybdenum in other applications, no?
Yes, it's used in a lot of different things. It's fairly abundant, so it's used in some steel alloys. It's used in some medicine. So yeah, there are all sorts of different uses for molybdenum.
I didn't know. Okay. Sorry.
Sure. All right, so this goes in here, just like that. If it'll fall off the tweezers. There we go. I'll try and center that as best I can. All right. So next up, I have my electrolyte loaded in a syringe right here. And what we're going to do... Oh no, that was not supposed to happen.
If you can just explain to us a little bit, what is an electrolyte?
Electrolytes are all different things. So electrolyte in general, you know what we're going to do, since this is not behaving the way I want it to, is we're going to get a new syringe.
There you go.
Working on the fly.
See what happens when you're on live streaming? Anything can happen.
So electrolyte is a liquid with some sort of ions in it. So your body needs electrolytes too, and anything that falls apart into ions, like sodium chloride falls into a sodium ion and a chloride ion, is an electrolyte. So you can use sodium chloride, you can use potassium chloride. We use much more complex molecules because magnesium is kind of touchy. It doesn't like nice easy molecules, but that's all right. All right, so I have my bottle of electrolyte right here, and we're going to pull up about 0.1 milliliters, so we really don't need very much.
Because later we're going to flatten it. It's going to distribute, no?
Yes. Yeah, it'll distribute. Our coin cells are pretty tiny. So it's just one of the benefits of working in coin cells. All right, so I'm going to put a couple of drops of this on our...
Don, can you see this?
Just wetting the material, and then we'll take a separator. So this is porous. This is just glass fiber, and it just separates the two sides while still letting the electrolyte and our magnesium go back and forth from side to side. So this goes right on top of there. And then we soak this with the rest of the electrolyte. So just distribute it all over. There we go, nice and soaked. All right, now for our anode, as I said, we're using magnesium metal. So it's been polished, since magnesium metal often gets an oxide film on top of it. Just like silver tarnishes, magnesium tarnishes as well. So we polished that off, so now it's nice and shiny.
And again, we're using magnesium because magnesium is the type of battery we're going to create.
Yes, exactly. One of the next generation chemistries that we're trying to work on is magnesium ion batteries. And the reason for that is that lithium, when lithium is charged, it has a +1 charge, and when magnesium is charged, it has a +2 charge.
It's like going to a wedding, so you have the +1.
Yeah, exactly.
Almost, yeah.
Or +2. So if you can substitute magnesium for lithium, then you automatically double your charge, right? 2 instead of 1. So if you could make a perfect replica, then you'd have double your energy. So
The same amount of density?
yes.
Double the power, same density.
Yes. Now we're not quite there yet. That's
Right.
what we're working on. But yeah. So I put another spacer on top of my magnesium metal, and then the last thing to go in is this little spring, and that just helps compress everything together and make sure everything's in good electrical contact. So I'll set the spring on top of there, and now I'm going to take the lid, put this on top, and just sort of squish it in and squish it all together. There we go.
I'm going to ask Don to come over here.
Yep.
I think at some point we're going to have the cool crushing piece. Well, not crushing. That's probably not a good scientific word to use.
It's close. But yes, we are going to put it in our coin cell press, and that will compress it all together. It wraps the top around the outside so that it seals it, and then we can, we'll be able to take it out of the box. Let me just pick this up. There we go. So there's our coin cell, unsealed. This goes right in here. There we go. And we turn it on, and the press does all the work for us.
And we have just made a battery.
Yes, we have.
And so once it's done here, what's the next step?
The next step is taking it out, putting it on one of our cycling machines, and running tests.
So that's what we're going to do. We're not going to take this one because we've already got it set up. We've pre-planned these things. So we're going to go with Lei to the battery recycler. Thank you, Krista. And we're going to see how batteries are cycled to test.
So here's another point. This is what Krista just showed us. She made a coin cell like this.
So everything that we just talked about is just in that little piece. So this is where we are now is we have just come from the glove box, and let's take a step back. You're watching Argon at Lunch. I'm Justin Bro, and this is Lei Cheng, and we're talking about next generation batteries. What's the process that you go through to create them and to test them? And so we just came back from talking to Krista, who creates batteries. She takes the information that Lei gives her and creates the actual battery. And now we're in the battery cycle room where they test the battery. So if Lei, you want to take that from there.
Right. So here's a cycler. If you can zoom in a little bit, you can see the coin cells are put into these channels here. So what this cycler does is actually it charges and discharges those coin cells that Krista just made and try to capture the voltage profile of these cells and see at what potential they give out the charge, and also to look at how you can go through different cycles and see how much energy you lose per cycle. And it also captures how much energy you store in this battery, obviously.
How many cycles does it go through?
Oh, it depends on the cell. So ideally, you want your battery to go, for thousands or tens of thousands of cycles for at least the electric vehicle, right? For cell phone, maybe, So
for me, 5,000.
You know how your cell phone eventually, after you have it for a couple of years, it only lasts you maybe about 4 hours. Well, at the beginning, it lasts you for like a day, and just because there are some undesired side reactions that happens in the background, eventually you lose the activity of your materials. So this is one of the machines we use to just cycle it through and see how much energy you have and how much energy you lose per cycle. And this is just one of the smaller scale machines. As we said, we talked about the battery group here at Argonne is really large, and so we have actually a P&D even much bigger room with hosted a lot of these machines that has maybe about like 1,500 channels.
Wow.
That you can run and test batteries all at the same time, and sometimes at controlled conditions, different temperature, for example, because your battery is going to behave very differently on a hot day in Arizona versus in a cold day, winter day in Chicago. So yeah.
I don't think anything works well on a cold day in Chicago. You agree with me? So we're going to move out here. And so if you just joined us or you come a little bit later, we talked about how to basically think about and design next generation batteries. And Lei has done an excellent job helping us out. But I sort of feel like I want to sort of wrap it up a little bit. So we're going to come over here. And Don, if you want to just get a shot of this computer screen. And this is a basic summary of the process. And so, Lei, do you want to take us through this?
Yes. So here, this graph shows you we have a database of the molecules or materials we wanted to study. So we do the screening through a high-throughput computation with our supercomputers located all over the country. And then we compute properties of each candidate and evaluate them. And eventually, we go down this funnel. Some of the candidates that have the properties that don't meet the criteria will be eventually eliminated. So at the end of the funnel, we have a much smaller and better set of materials to work with. So I will just send these information to my experimental collaborator all over the country. Krista here is one, and then we have collaborators at UIUC, MIT, and Berkeley. And I should say that this part of the work, computational work, is also done at Berkeley as well. So then they will select some of the materials and synthesize them. And before they put it into a cell for testing, they will use different characterization methods and tools to analyze and make sure they can identify the chemicals they made and make sure that's what we intended to make, and then put it into a cell that Krista just showed us how to put that material into a cell, and then we take it to the cyclers for testing. And we also have a constant feedback loop. So sometimes she'll come back to me, ask me to, so I just observed something that's unexpected. Can you help me understand why this happens? I can use my computational tools to do that and to do a more in-depth study of the materials on her demand as well.
Excellent. So now we're wrapping up at this point, but I have to ask one of our guys, hey, Mike, do we have any questions?
Yes, we do, Justin.
All right.
We have a few questions for you, Lei. Imdadul asks, is the battery you work on specifically for electric vehicles? We have Imdadul who asks, is the battery you work on specifically for electric vehicles?
Yes, big part of our research is to study batteries for the electric vehicles, yeah.
Chell asks, do you drive an electric vehicle?
Oh, okay.
I personally don't. I love Tesla Model S. I test drove it. I just cannot pay the $70,000 price. I mean,
And that's the point, right? That's why the research is going on, to bring that price down so we can afford it. Thank you, Shell, for that question.
I want to walk the walk. It's just with the scientists' salary, I can't.
Guru Prakash asks, how long till lithium-air batteries become a reality, and can you use molten electrolytes for lithium-air, which usually offer high rates, where lithium-air suffers from those lower rates?
Yeah, so lithium air at the beginning stage, so lithium air is something that we studied. We think is fundamentally very intriguing subject to study on, but later on we wanted to come up with a battery system for testing a prototype. We kind of didn't emphasize the lithium air, so that's not something we are actively working on as a system right now.
But as a battery, so if I get this right, you have a battery made of air? Is that essentially what it is?
Not just one part of the component is air. Yeah, it uses air, it reduces oxygen in air to be
power
more
the vehicle.
specific. Yeah.
Do you have any more questions?
We do, Justin. A few more. Some more technical questions. Mike asks, can the structural design of a battery affect its performance?
Yes, definitely. So that's more on the engineering side of things. So if we can walk over here a little bit, sorry. So we see that the research cell normally looks like this. It's a much smaller cell. It's a coin cell. What we have here is what we call a pouch cell. So if we were to put the same type of materials, exactly same chemistry into those two cells, they look more or less the same because they have the same chemistry. But in the meantime, there are some differences as well because the materials and also charges will distribute very differently in these two configurations. So yeah, that is going to look different.
Very good question.
Yeah.
And they keep coming in, Justin. Cindy asks, when you assess candidate materials for batteries, do you consider the abundance of the material?
So abundance of the material, when we first decide on what type of battery concept we need to work on, that's already been taken into consideration. So for magnesium battery, for example, it's earth abundant, it's cheap, right? This is one of the reasons, other than, it carries double the charge, one of the reasons we choose to study magnesium battery. And another example is lithium sulfur battery. Lithium sulfur doesn't cost anything, so we choose to study sulfur battery. But during the screening process, when we, come up with new materials to work with that could potentially get us the high energy density we want, we're not terribly concerned about the cost at this point, especially when it comes to organic molecules, right? I mean, it might be expensive now, but if there is enough demand and there's, scale up, then it'll become cheaper.
Excellent question. All right, that's our last question. And Lei, I want to say thank you so much. This has been great. You've been watching Argonne at Lunch. I'm Justin Bro. This is Lei Cheng. You stay classy, Argonne.